Yeah. So our guest is Lars Grüne. He's a professor in Bayreuth. This is in, well, it's not Eastern Germany, but very close to Eastern Germany, very close to the Czech border. It's a nice little town. I've been there for a while. You may know Bayreuth because of the Bayreuther Festspiele with Wagner and so on. This is kind of famous, so if you ever come by. Yeah, so he's done a lot of work on control theory, stabilization, attractors, whatever you can imagine, Bellman functions. So the entire spectrum, with probability, without probability. He's pretty well known in the subject, and so I thought would be a good idea to invite him to our seminar. And today he's going to speak about the Turnpike property, which is, as far as I know, a property of a control system as time tends to infinity. And so if you want to make something work for a very long time, this is an interesting property to examine for your control system if you have to control this for a very long time, and so basically up to infinity. So then I leave it to you and listen.
Thank you very much, Janos, for the kind introduction, and thanks to all the organizers for inviting me to this seminar. That's a great pleasure to talk about some recent results, and recent here means results from the last couple of years, because this is a bit like a survey where I want to highlight some of my and our results from the last years. And for this reason, this is also based on work with a couple of collaborators. There's Roberto Guglielmi, who's now in Waterloo in Canada, Matthias Müller from Hanover, Manuel Schaller, a former PhD student of mine, who's now postdoc in Ilmenau. Anton Schieler is my colleague next door. He works on optimization with PDEs, and Marlene Stieler is a former PhD student who now works with a big chemical company in Germany and uses some of the things that she learned and did during her PhD now in an industrial context. Yeah, so here's the brief outline of my talk. I will first tell you a little bit about what this Turnpike property is, right? What this is all about. And then I will talk about the relation to other properties that control systems have. And I'm doing this more from a system theoretic point of view. So I will introduce a couple of properties that are well known in mathematical systems theory since 50 years. And I will show you how these relate to the Turnpike property. And in the end, I will tell you a little bit about the reason why I became interested in this property in the first place. This is a particular algorithmic method called model predictive control, and for understanding why this method works, this Turnpike property turns out to be really very important, and this is what I'm going to talk about in the last couple of minutes. I will partially work with discrete time systems and partially with continuous time systems in this talk, and I will start for the first part of my talk with discrete time systems because some of the considerations simplify a little bit in discrete time. So what I'm looking at here is a control system. So U is the control that acts on the system at time instant n, and it's plugged into this map F, where also the state at time n is plugged into, and from this pair state and control, we get the state at the next time instant n plus 1, right? And then we have some initial condition, which is either called x, sometimes x naught, depending on the context. And this is a very general setting in the sense that we can work on arbitrary normed spaces. We could even go to metric spaces for many results, but this generality, I think it's not possible for today's survey talk. There's a brief notation for this, which is simply x plus is equal f of x and u, where x plus is the state at the next time instant. And the interpretation that I already mentioned is that x u of n is the state of the system at some time, some real time tn. And un is the control that acts from time tn to time tn plus 1, so on this time interval. And then f is usually the solution operator of a controlled ODE or PDE, could also be a genuine discrete time model. In my very simple examples that I use for introducing the Turnpike property, I will use genuine discrete time examples. We will go to PDEs then later in the talk. Yeah, and of course, it could also model a numerical approximation. So now what's the Turnpike property? The Turnpike property describes the property of optimal trajectories, and here I have to correct Janos a little bit. It's actually optimal trajectories for finite horizon optimal control problems. There is an infinite horizon version, but I'm not going to use this very much in this talk. But the important thing is that the length of the finite horizon, which is this capital N here, this is allowed to vary and to become arbitrarily large. And this is, so in this sense, it's an infinite horizon thing, but not in the sense of that we have an infinite sum here, but that we have a sum that can be arbitrary long, could have arbitrary many terms. So L is called the cost function here. It gives you a real value for every state control pair. And we simply sum up this cost function, then we get another real number. And then we minimize this for each initial condition X with respect to the control sequence U, right? So U0, U1, U2, and so on up to U capital N minus 1. And this is usually subject to additional constraints. So the state is required to stay in some set X with this double bar here and U in some set U. And the Turnpike property now describes a property of the optimal trajectories, right? So the optimal solutions that we get. So every optimal solution gives you a sequence of states, and this is the trajectory. And the informal description of the Turnpike property would be that any optimal trajectory stays near some equilibrium. So equilibrium is a constant solution of the system most of the time. And before I formalize this in a mathematical way, I would like to illustrate this property by two very, very simple examples. And the first simple example is simply that we have this dynamics here. So x plus is equal to x plus u. If we do not use any control, so if we set u equal to 0, the state always doubles. And you see that except when you start in the origin, this immediately gets unbounded and grows either in the positive or in the negative direction. But we have constraints here. In particular, this constraint is important here. So we would like to keep the system inside this bounded interval, which means that we have to use some control action. Without control action, this would never happen for a general initial condition. And then the optimal control problem is to do this with a minimal quadratic control effort. So we want to minimize the u squareds so that the squares of the control values be used for this purpose. So in a way, we want to minimize, if you want, it's a very simple problem where we want to keep the state bounded with minimal energy in a sense, or minimal effort, maybe it's the right thing.
No et molesta?
Yes, please.
Com que no entenc res, és com si tingués música.
Was that a question? I couldn't get that. Maybe not. Okay, so I will continue. If it was a question, just repeat it later. And what you can already analyze is if you look at equilibria, so all the points where 2x plus u is equal to x, then you can find out which is the best equilibrium, which minimizes the control effort, and this is actually the origin, right? Because at the origin is the only point where I do not need to spend any control effort to keep the system inside the set x, right? Because it will stay there by itself. So the optimal trajectory should probably also stay near the origin. This would be like some guess that one would have, and this is what the optimal trajectories do. Here we have the initial condition, here we have the origin, and then what you see is that the optimal trajectory goes in the direction of the origin for 2 steps, but then it turns away and goes to the upper bound of the admissible interval, right, which is exactly the value 2. And this is quite clear because at the beginning, well, it's cheaper to go down and then up again instead of just staying constant, because the control that we need to keep the system inside here is cheaper in the sense of the cost function. But after a certain while, the optimizer simply sees that by just setting the control to 0 and letting the system go, we do not violate the constraints, and this is the cheapest way to do it. Now let me increase the horizon now. And what we see is then that we get qualitatively the same pattern, but quantitatively something happens because the optimal trajectory moves further and further down and stays longer and longer in the vicinity of this equilibrium here. And this is precisely the Turnpike property. So we stay near this equilibrium most of the time, and most of the time means except for the beginning, which is clear because we start away, we have to first go there. And in the end, which is also clear from the structure of the problem, because this is the cheapest way to keep the state in the set between -2 and 2. Okay, here's a second example. This is one of these macroeconomic models that were fashionable in the 1970s. And let me briefly explain what's happening here. So how do we put together these dynamics? So what we have here is we have two variables, again, X and U. X is the invested capital that you invest in some company, for example. And U then, this is immediately clear from the very, very simple dynamics we have here. U is the investment in the next time step, right? So X, K plus 1 is equal to U of K. And then this term, A times X to the power of alpha, this is the capital that you get in return after one time step. And that should be usually larger than what you invested. So it's your investment plus the return. And then this AX to the power of alpha minus U is everything that you do not reinvest. So this is the capital you can use for consumption, right? Where you can buy things or make holidays, whatever. And then this logarithmic function here is the typical utility function that quantifies the benefit that you get from consumption. And since we want to maximize this, but my problem was a minimization problem at the beginning, I put a minus in front. So this is how this term here comes. So we would like to keep investing over a certain horizon and spending money, but the only benefit we get is from spending money, right? Only from spending money we get a positive benefit. Again, you can analyze optimal equilibria here, and you actually see that the optimal equilibrium for infinite horizon is exactly this point, right? This is the best steady state where you get the best effort in terms of the best reward in terms of this cost function here. Now, what happens if we optimize over a finite horizon? So the blue line again indicates this optimal equilibrium. And 5 units is the initial capital, and it's completely clear due to the structure of the problem that in the end we end at 0, right? Because it's always optimal to spend all your money in the end. There's no reward that you get from having any money left at the end of the horizon. And more or less, we spend a lot of money in the first time step, then we spend a little slower, and then we spend again a lot of money in the last time step. And now, if I increase the time horizon, then we see that the spending gets less and less in the middle. It's not 0 because we do not see the return on investment here, but the investment basically remains constant, and it remains constant equal to this equilibrium value. And again, we see the Turnpike property, so the optimal trajectory starts here. It stays near the equilibrium for a long time and then moves away in the end, because at the end, at a certain point, we decide to spend the rest of the money and clear the account. Okay, this is in pictures what the Turnpike property is. Now the question is, what is it formally? How do we formalize this mathematically? And this is the picture from the first example. What we do mathematically is the following. We put a neighborhood around this equilibrium, which is this blue region here. And then we simply count at how many time instances these optimal trajectories are outside the neighborhood. And if you do this here, you see that there are never more than 8 points on each trajectory out of the blue region. So if we count, for example, for this one here, we have 1, 2, 3, 4, 5, 6, 7, 8, right? 8 points outside the blue neighborhood. And no matter how long I make the horizon, it will never be more than 8 for this example and for this choice of the neighborhood. So, and this is exactly how we formalize the Turnpike property. This should happen for any neighborhood, no matter how small I choose it. But of course, the number 8 then will depend on the size of the neighborhood and also on the initial condition. If I start very far away, of course, it will take longer and take more points, more time steps to go down. Yeah, so this is a formalization then. We assume that we have an equilibrium, so a point which is mapped onto itself if I use a suitable control value. And then the Turnpike property says, let's start here. The number of exceptional points where we are outside the epsilon neighborhood is bounded by a certain number, and this number depends on 2 parameters, rho and epsilon. Rho is the distance of the initial condition from the equilibrium, and epsilon is the size of the neighborhood here, right? So if I fix the size of the neighborhood, if I fix the initial distance, then the number of points which are not in the epsilon neighborhood must be bounded by a certain number. And this is this number 8 that we saw in the example. And if we move to continuous time, then you would replace this number of exceptional points by the Lebesgue measure of the exceptional points, right? This is everything that changes if you go from discrete to continuous time. Little bit of history. This is a quite old property. It was observed by, well, the pioneers who worked on economic models on exactly these kind of optimal investment problems. These were Ramsey and von Neumann in the 1920s and 1930s. The name Turnpike property was coined a little bit later in the 1950s by these three very famous mathematical economists, Dorfman, Samuelson, and Solow. And the name Turnpike stems from the fact, I think Turnpike originally is like a barrier that can be moved up and down to block a road. But particularly in the northeastern part of the United States, Turnpike is also synonymous for a highway or a motorway. And this is what the people had in mind when they used the name Turnpike property, because this typical picture reminded them of a car that drives on a highway to reach a goal. So you have some place where you come from, some place where you go to. And what you usually do is you take smaller roads to the next highway, you enter the highway, you drive on the highway because this is the fastest way to proceed. Then you take the exit and go to your goal, right? And this is where Turnpike property comes. You could also call it highway property or motorway property. That would be the same meaning. It was extensively studied in the 1970s, and a very good account of this development was given by Lionel Mackenzie in 1983. I should say that this paper is not so easy to read for people who are not in economy, because there are very often mathematical arguments are mixed with economic intuition, and it's not so easy to really get the mathematical rigorous flow of arguments from this article. But definitely this was non-trivial and very sophisticated work that was done. And then in recent years, say since about 7-8 years, there was some very much renewed interest that was fueled by two different developments. So one development was model predictive control, which was also my reason to look at this property. And I will talk about this a little bit in the last part of this talk. And the other renewed interest was by people who came from the optimization with PDE community, because they realized that for partial differential equations and optimal control problems with partial differential equations, the Turnpike property is really ubiquitous. It appears in so many different problems, and it can systematically be used to simplify the solution process for these properties. Because basically, all you need to know is, how do I get to the equilibrium in an efficient way? And how do I get to my target point from the equilibrium, if there is a target point? Or how does the last piece look? And instead of computing a solution on a very long horizon, it suffices to compute two short solutions, and then you lose the equilibrium, right? And this is much easier in many cases. And yeah, this is exactly the second part, the synthesis of optimal trajectories, which is actually not an invention of these days PDE optimizers, but actually goes back at least to the 1980s. And I think there's also an earlier paper from the 70s, which I still have to look up, where this has been used. And the economists were mainly interested in structural insights, right? Optimal economic equilibria were and are a really important topic. And this is what they would like to know and analyze. And this is why they were interested in this property. But in this case, it's really the synthesis of optimal trajectories and model predictive control, which are both more algorithmic reasons to find this property interesting. It's closely linked to a concept that has been very, very important in mathematical control theory since the early 1970s. So it's exactly this year, 50 years ago, that this seminal paper, actually a series of papers of Jan Willems, appeared. And this is also the first property I would like to explain, the first relation I would like to explain when I now talk about systems theoretic properties that are linked to the Turnpike property. And this is dissipativity, strict dissipativity, and something called detectability, which I will talk about. Yeah, so the optimal control problem is called strictly dissipative. This is the definition. On a certain set at an equilibrium, if there exists a certain function lambda, and you can think, if you know Lyapunov functions, then you have a certain idea what this function lambda is. It's a little bit like a Lyapunov function, not exactly like that, but something which is structurally similar. Because we have the following inequality. If you think of lambda as some kind of very generalized definition of an energy which is in the system, then what this inequality says is that the energy after one time step is less or equal than the energy at the point where I started, plus something which is provided by the cost function in a shifted way where I subtract the equilibrium value. minus something which is depends on the distance from the equilibrium. And dissipativity would be without this alpha. It simply says that the amount of energy does not increase over what was already there and what is provided. And strict dissipativity says, no, actually the energy in the system always decreases a little bit, except when we are in the equilibrium, because then this term is zero. I should tell you what this alpha is. Alpha is a so-called K function, and they always look like that. They map the non-negative reals to the non-negative reals. They are continuous, strictly increasing and zero at zero. So a typical graph of a K function would be something like this, which means that this with the minus sign here is negative whenever X is not the equilibrium, right? So outside the equilibrium, we always lose a little bit of energy in the system. This is what strict dissipativity requires. Yeah, and the fact is that whenever we can control our system sufficiently fast to the equilibrium here, then strict dissipativity immediately implies the Turnpike property. And the idea for this proof can be found in this book by Carlson, Ori, and Leisarowitz from the early 90s, but under somewhat stronger conditions than necessary. And in this particular form, I rewrote it, but this was not a major task in 1913. And I can give you actually a sketch of the proof in 2 lines here, because the idea of the proof is if we can control the trajectory quickly to the equilibrium here, then this term here, the L along the trajectory, so the cost along the trajectory minus the cost in the equilibrium, will go to zero very fast. And the sufficiently fast actually requires it that this can be controlled to zero so fast that this sum here is bounded by a constant independent of K, right? So basically that we have a converging series here. This is the condition of sufficiently fast stabilizable. But if this is the case, then we can rewrite, I mean, this difference is exactly this difference here. So we can use this inequality to conclude that then also these terms here, when we sum over the other 3 terms, must be bounded by C. And then you see that there's a telescopic sum involved by these 2 terms, where only the last and the first value remain. And now this must be bounded by a constant independent of K, which means that this series must also be convergent. But if this series converges, then alpha of this term must go to 0. And if alpha goes to 0, then also the norm must go to 0, which means that X star, it must not go to 0. It must be 0 for, it must be small for a long time, right? For many time instances. And this is exactly the Turnpike property, because then we are close to the equilibrium most of the time. It's not an infinite sum, so it must not converge to 0, but it must be 0 or close to 0 for a long time. Yeah, this of course inspired me to ask the question, well, how much stronger is dissipativity than the Turnpike property? And it turns out not very much, because under a certain controllability condition, which I will not go into details now, it actually turns out to be equivalent to a robust version of the Turnpike property. So it's a little bit stronger than the classical Turnpike property, but not very much. This robust version requires that not only the optimal trajectory, but also near optimal trajectories exhibit this Turnpike phenomenon. And dissipativity can now links to other very classical system theoretic properties. If we look at something which a particular class of optimal control problems, namely the so-called linear quadratic problems. And this is this one here. So we look now at dynamics which are linear. So X plus the next state is equal to AX plus BU, A and B matrices of appropriate dimension. Everything finite dimensional now. So now we are in Rn. And the cost is a sum of quadratic terms and linear terms depending on X and U. Right, and this Q here is a positive definite matrix, and by Cholesky decomposition we can always write it in that form. And R should be a positive. Q is positive semi-definite, and R is positive definite here. And then we can show that strict dissipativity, when we have no state constraints, so if we look at the whole Rn, holds if and only if this pair is detectable, which means that a certain number of eigenvalues of A, which are these which are always mapped, for which the eigenvectors are always mapped to 0 by C, they are called unobservable, so we cannot see them in the cost function because they are always 0. They for these eigenvalues, the corresponding eigenvectors, the corresponding eigenvalues must be greater or equal 1. Sorry, must not be greater or equal 1 in modulus. So there are no such eigenvalues. This is a very classical condition that is known to be needed if you want to set up an optimal control problem and want to make sure that the optimal trajectories do not go off to infinity. On a bounded subset, this is very interesting. On a bounded subset, we have a weaker condition, and the weaker condition is that we only need that there are no unobservable eigenvalues as modulus equal to 1. So suddenly, if we have a bounded subset, we can allow for eigenvalues which are greater than 1, which actually create instability. And this sounds weird at the first glance, but the explanation is that if we have these eigenvalues, then we have to counteract with a control. And because this R matrix is positive definite, we will see this in the cost, right? So they are not undetectable anymore, right? You can see them in the cost because in order to maintain the constraints, you have to counteract with the control, and this shows up in the cost. So this is why we get this weaker condition on bounded subsets. This is in discrete time with the usual changes that, of course, we now then look at the real values, at the real parts of these eigenvalues. The results also hold in continuous time. And what we are currently working on is an extension to infinite dimensional systems. There are 2 first papers which you can get on my website, where we started to generalize some of the results which are behind these if and only if characterizations, also for partial differential equations. So infinite dimensional problems where we have differential equations here instead of discrete dynamics. In the interest of time, I will skip this nonlinear detectability and rather go on to something which is another very interesting connection, and this is the connection to sensitivity. I think some of you here are interested in optimal control, so you know what sensitivity means in optimal control setting or in optimization. Generally, it means the question, how do optimal solutions change if I vary a parameter a little bit, right, in the optimal control problem? How do the optimal solutions, which in our case are always these trajectories, how do they change if I play a little bit with parameters? And this has a relation to the Turnpike property, as we will see in a couple of minutes. And what I would like to do is I would like to present this in the setting where we prove this, which is first of all in continuous time. We still restrict ourselves to linear equations, but we do this in a very general setting because we consider linear PDEs, so-called linear evolution equations, which are equations that are written in this abstract form, but now Y is not a finite dimensional state anymore, but actually phi comes from a Banach space. So, and this A is not a matrix, but an operator, B2, and A is an operator that generates a strongly continuous semigroup, right? So if we just have the differential equation without the B and without the F, then the solution would be a semigroup called capital T of T. X is an appropriately chosen Hilbert space. F is a source term here that can, of course, be nonlinear on the right-hand side. And we have an optimization objective, which is again quadratic. Now, of course, since we are in continuous time, it's an integral and not a sum. And we have 2 matrices C and R, which play exactly the same role as before. So C basically says how we weight the state, and R says how we weight the controls. And U and Y are appropriate Hilbert spaces where the U and the Y variable live in. Sorry, I'm somehow mixed up. What is Y? No, Y is actually here the space where C maps to. Sorry, this is a bit, the notation is not completely good because Y lies in X and CY lies in Y. Anyway. Yeah, and R should be an elliptic operator, which replaces the positive definiteness that we had in the finite dimensional setting. Yeah, we have to make sure that we get a solution theory, and I think the most general framework that is available for this is the framework of admissible operators, which I cannot explain in the interest of time, but this is a condition on the operators B and C for which we can get solutions to this, which also makes sense in this integral if we map them with C. where we get still integrable functions here. So B and C are assumed to have this property, and I should mention that this allows to use unbounded operators, which is very important if we want to use boundary control or boundary observation, where, for example, B is an operator which only acts on the boundary of the domain where we look at the, where we could consider a PDE, for example. And then we already immediately get to unbounded operators, and this framework allows to do that. And then we can use a solution concept, which is called the mild solution. This is the standard solution. It's a weak solution concept, which is standard in this framework. Now, if we look at this optimal control problem, we can actually write down an optimality condition, which is derived from Pontryagin maximum principle, or in this case, we should say minimum principle, because we have a minimization problem. And in a very compact operator form, we can write it like this. So we have a big operator M, which includes the co-state equation. It includes the terminal condition on the co-state variable. It includes the state equation. And it includes the initial condition for the primal state, right? So these ET and E0 are point evaluation operators, which are defined like that. And this is the right-hand side then depends on the data of the problem. And of course, on the terminal condition for the lambda, since we have no terminal constraints, is 0, and the initial condition for y, which is now called y naught here. And now we look at the perturbation. This is where sensitivity comes into play. And I would like to perturb the two equations that are, the two partial differential equations that are encoded in this operator by small perturbations epsilon 1, epsilon 2, which are functions from an appropriate function space, so that this is well defined. And then I would like to look at the difference between the perturbed and the unperturbed solution. And by a very simple argument and using the linearity, one sees that this delta y and delta lambda are determined by this partial differential equation, again written in this compact operator form. And now we would like to understand how much the epsilons here influence the difference between the perturbed and the unperturbed solutions. And we do not only want to estimate this uniformly over the time interval that is here from 0 to capital T, but we would actually like to understand how the influence changes over time. And the idea that we use here is we use this a very simple inequality. We just invert M, bring it to the other side, and then use some induced operator norm here. But the trick is that we apply exponential weighting. And the abstract theorem looks like this. What we do is we define an exponential weighting, exponentially weighted norm of these perturbations here. And then we assume that the norm of this inverse operator M is bounded. And we look at different norms here. And the important assumption is not that it's bounded. This is something you can easily prove. But the important thing is that it should be bounded independently of how long the interval is that we look at, right? And well, let's just keep this as an assumption for the moment. And if this assumption is satisfied, then we can get exponentially weighted inequalities for the difference in the state, in the co-state, and in the control. And since these are really kind of difficult to digest at the first glance, I have rewritten one of these in a simpler form, because if we plug in, say, the one norm here, so the L1 norm, and the continuous norm, so this is the estimate from down here, we can rewrite the second inequality in this form. And what you see here is that we have an exponentially decaying term here, which means that, for instance, if I plug in a very small t here, say t equal to 0 or close to 0 here, and I only have perturbations which act for large t, so perturbations are 0 for a long time, and then suddenly they get large in the end, then these large errors for large t here, large means close to capital T, they are actually exponentially damped for small times. So we have a damping of perturbation through the solution operator. And this is interesting and actually not really expected, because we have this maximum principle always gives you a forward and a backward equation, and actually perturbations could be transported in both times. And there are, but they are exponentially damped during that procedure. Yeah, so I had this assumption, this t-independent bounds on these norms, and it turns out that this can be achieved. And again, what we need is certain stabilizability and detectability. In the infinite dimensional setting, we need to make sure that it's exponential, which is a particular form of this. And if this is satisfied, then all the above norms are actually bounded independent of t. And this is definitely the hard part of this analysis. The first theorem is quite easy and quite straightforward. Here you really need to use some tricks, and I should credit my former PhD student Manuel Schaller for this. He really worked out all this, and he was the mastermind behind this result. Yeah, what does all this have to do with the Turnpike property? And this is a result which is independent at its own right, but at the first glance, there is no real relation to Turnpike. Well, the thing is that we can do now a very similar thing. Instead of perturbing the equations, the state and the co-state equation, we can also perturb the initial conditions. And if we do this and do essentially the same analysis as before, but with a different exponential scaling, and now define the delta as the difference between the optimal solution and the optimal equilibrium, and the same for u, then we get inequalities of this type. And again, with these written in this form, it's not so easy to digest. So I will rewrite the second one to something which is formally weaker, but much easier to understand, which is this inequality here. And what this inequality says is basically that we have a term here, which has these two exponentials. And these exponentials will be small if t is away from 0 and if t is away from capital T. Which means that if you plot this expression, you get something which goes down to 0, then stays 0 for a long time, and then goes up again. This is precisely the estimate we want for the Turnpike property, because it says that the state and also the co-state are close to the equilibrium, because this is this difference here, close to the equilibrium, except maybe at the beginning and at the end. And actually, this is a stronger version of the Turnpike property than I had before, because we have this exponential bounce here, which gives you additional information about how fast the solution goes to the equilibrium and goes away. And this is what is called exponential Turnpike. Okay, this relates to several results in the literature over the last couple of years. And actually, I think it's so far the most general setting under which this kind of Turnpike result was proved, because we can really work with unbounded B, unbounded C, and also we have very weak assumptions on A. So for example, this is one of the few properties which can be applied to general hyperbolic equations, like the wave equation, for example, which is not true for many other results. So it applies to hyperbolic PDEs, it applies to boundary control and observations. We also have a local version for nonlinear systems. And well, maybe at the end of this part on system theoretic properties, I would like to add one sentence which explains the difference between the two approaches that I showed you. So I had the sensitivity-based approach, which works with operator estimates, and I had this dissipativity-based approach, which works with this storage function lambda, this Lyapunov-like functions. And indeed, if you compare the Turnpike property with asymptotic stability, then the first approach that I showed you is actually very similar to what you do with Lyapunov functions. It is a kind of Lyapunov functions, while the sensitivity-based approach, it depends on spectral properties of these operators. So it's very, very similar to spectral conditions for the linearization. So the two approaches that we know for proving stability or asymptotic stability of ODEs and PDEs, Lyapunov functions on the one hand and spectral analysis on the other hand, they also resemble these two approaches, dissipativity and sensitivity based for analyzing or ensuring the Turnpike property. Okay. For the last 10 minutes, I will talk about a little bit why all this became interesting to me. And this is model predictive control. This is something I've been working on since almost, I would say, well, more than 10 years now. Something which is I find very fascinating, because it's a very, very simple idea to solve very, very difficult problems. Yeah, so what is the very difficult problem? The very difficult problem, and I'm now returning to discrete time, the very difficult problem is such an infinite horizon optimal control problem, which I would like to solve. And of course, like for finite horizon problems, you can write down necessary optimality conditions, but they are difficult because you still have infinite terms. You have to truncate somewhere, or you have to make assumptions that things fade out, become less important in the future, that you have some exponential decay. So it's always, you always have difficult problems to somehow make this tractable computationally, right? If you're looking at a feedback control problem, which is the more interesting and also practical and more relevant case, you have to work with dynamic programming, which is known to be prone to the curse of dimensionality, which means that if the state dimension is larger than, say, 4, 5, 6, it's really, really very hard to solve these problems. And model predictive control is a really simple idea to solve these problems. Instead of directly trying to solve these infinite horizon problems, minimizing this infinite sum, we would like to iteratively, we solve iteratively a couple of finite horizon problems. And if n is not too large, this can nowadays be done in almost no time, in milliseconds, right? So I think people who do these algorithms are even down to below milliseconds for reasonably sized problems. So this is really very, very, very quick. So even if you want to have to solve many of these problems iteratively, this can be done in a reasonable amount of time. And even for fast processes, this is now a really valid or viable, I should say, viable solution. Okay, how does this work? How can we use finite horizon problems to iteratively to solve an infinite horizon problem? Well, the idea is the following. We have some initial conditions, and now we solve the finite horizon or open loop optimization. And these are the so-called predictions from which the name model predictive control comes from. It's just an optimal solution over a finite horizon. Here we have 5 steps, right, from 0 to 4. 4 steps, 1, 2, 3, 4. And what we do is we use the first step now to generate our so-called closed loop trajectory, which is called XMPC in what follows. And then we get the new initial conditions, and now we again solve a finite horizon problem with 4 steps, but now starting here and at time 1. So we get a new optimal trajectory with a finite length. We again follow the first step here. We solve again, we follow the first step, we solve again. And now you see that by solving this finite horizon problem over and over again, we can generate an arbitrarily long solution. And this solution, which consists always of the first pieces of the finite horizon problem, this is our candidate for the infinite horizon. Well, not optimal, but maybe near optimal solution, hopefully. This is what we would hope. And this is actually true. And the connection to Turnpike is, if the finite horizon problems have a Turnpike property, then we can rigorously prove that the solution that we get from this procedure is near optimal for the infinite horizon problem. And before I make this, I show you the theorem that explains in which sense this is true, I would like to show you how this works in an example. And basically the whole analysis which is behind exploits that this red closed loop trajectory approximately follows the first part of the black predictions to the equilibrium, but then they do not follow the second part of the black predictions, which go away from the equilibrium. And to show that this really happens, let me show you the example, the second example I had in the introduction with n equal to 10. So this is, I have omitted this blue line here now, which would be somewhere here, right? This optimal equilibrium. And this is this optimal investment problem where you spend your money in an optimal way in terms of this cost function that is specified here. So we start with a certain capital, we move that down to this level, stay here for a while, and then spend all the rest here. And what one knows from, because this is a very well-studied problem, is that the infinite horizon optimal solution would actually go down here and then stay at the optimal equilibrium. So it should continue here and never go down. And now let's apply model predictive control. So we follow the first step. We optimize again from here. What you see is that there's almost no difference in the first steps between the first and the second solution. But of course, this arc here in the end is shifted now by 1 time step. We follow that, we compute again, we follow that, we compute again. And then you see that the red line, which glues together all the first pieces of the finite horizon optimal trajectory, in fact, stays near the equilibrium. It never follows this leaving out because this is always too far in the future. And it has qualitatively exactly the property that we would not only expect, but what we can prove by other methods for the infinite horizon optimal trajectory. Now, what can we rigorously prove? And this is from a paper with Marlene Stieler from a couple of years ago. Let's assume that we have an optimal control problem. I'm not assuming Turnpike only, I'm assuming strict dissipativity because this is the mathematical formulation that helps us. But as I already told you, this is basically, well, just a little bit stronger than assuming that the Turnpike property occurs. We need some regularity, which I will not comment on too much. It's a like kind of weak continuity condition in the equilibrium. If this would be like a uniform continuity condition if we omit this omega. With this omega, it's even relaxed. And if we have this, then we get three properties. The closed loop, so this red solutions that we get from performing this model predictive control algorithm, is actually semi-globally, practically asymptotically stable. It's approximately transient optimal and also approximately averaged optimal. And I would like to explain at least two of these in an understandable way, two of these properties, and I'm explaining the first two. And I'm doing this with a little picture. So let's look at the following. So here we have the state on the vertical axis and time on the horizontal axis. And the blue line is again the optimal equilibrium where we have the Turnpike property. And now what we can do is we can find epsilon1, which depends on n, which tends to 0 if n gets larger and larger. So the larger the horizon, the smaller this epsilon1 and the smaller this neighborhood will be. Now, practical asymptotic stability, the first of the three properties, means that if we look at this red solution, then it will eventually converge into this neighborhood. What it does then, we don't know. It can stay constant at a different place, or it can just go up and down or do something periodic. This is something we can't control, but what we know is it will never leave this epsilon1 ball around xe again. And since we can make this epsilon1 ball as small as we wish in principle by increasing the length of the horizon for the finite horizon problems that we solve. This is called practical asymptotic stability. It's practical in the sense it's as good as asymptotic stability because for practical purposes, whether we converge really to xe or only to a small neighborhood doesn't really make a difference. And now, what kind of optimality can we prove? For the optimality, we fix some time k, arbitrarily long, can be much, and typically this is much larger than the horizon n that we use in the finite horizon problems. So we pick some k. And then we, of course, there are many, many other ways than this red one, usually, to find this trajectory that starts in the same initial condition, but ends up in this small neighborhood here of the equilibrium, right? It could be that one, could be that one, could be that one. And now what the theorem says is that among all these trajectories that start up here and end up in the neighborhood, the red one here is the cheapest one, except for small error terms. So basically, the red one here is the best, except for the error term, which sums up with this k times epsilon1 plus epsilon2. If we make k large, then this term will be small. If we make n large, then this term will also be small. Typically, this epsilon decreases exponentially, or not typically, but in many examples, it decreases exponentially in n, and then we get something which has linear growth in k, but exponential decay in n, so this will be small, even if k is large and n is not too large. And yeah, this shows that among all these trajectories, we have that the model predictive control trajectory is the best one. And then we can also say something on the whole horizon, which is this average sense. I do not have a picture for that, but it's not only optimal up to some time k, but it's actually near optimal then in an average sense also for all the future times. Okay. Yeah, let me show you that this practical stability really happens, that we do not necessarily get true convergence to the equilibrium, but only to a neighborhood. And this is the first example once more, with now with a different initial condition, and we do MPC here. So the black ones are the finite horizon problems that we solve. The red ones are always the first pieces glued together. And we see that the trajectory converges nicely down to the 0, which was the optimal equilibrium here, but it never really reaches 0, and actually convergence stops in some distance of the optimal equilibrium. So this is the merely practical asymptotic stability of the 0. It does not really go there, it only goes to a neighborhood. And what our theorem says is if we increase n, then the distance between the red solution, or the limit in this case, which exists of the red solution, and the blue equilibrium should become smaller. So let's repeat this for n equal to 10. This is this one. And then what we see is that we have, again, the same qualitative behavior, but now quantitatively we go much further down because all the individual solutions go much further down. And we end up at an equilibrium which is, well, not exactly the blue one, but very, very close. And here you really see this relevance of this practical. So you decide how close should I end up, how large distance do I allow? And then if we adjust n appropriately, and assuming that, of course, then this is algorithmically still feasible, we can get this. And I should mention that maybe some of you have heard about model predictive control before. There's always a technique which is very, very interesting, that you can actually improve the behavior of this closed loop solution by employing so-called terminal conditions. They are difficult to design, but if you know how to design them and can do that, you can actually gain a lot. And I should say that some of the results that I presented here can actually be improved. In the interest of time, I will not tell you details, but both the stability and the average optimality, and also the transient optimality, you get better estimates if you employ terminal conditions to your finite horizon problem. But again, I will leave out details because I'm already at the end of my time. Okay, so let me wrap up. What I wanted to tell you is that the Turnpike property is a property of optimal trajectories that you can find in many, many optimal control problems. If we assume stabilizability or reachability or controllability, so some nice properties of the underlying control systems, then it is closely related to properties which are well known in systems theory, like strict dissipativity and detectability. We could show that it's actually can also be seen as a particular instance of a more general sensitivity property, and this even works in an infinite dimensional linear evolution equation setting. And if this Turnpike property holds, then model predictive control provably provides approximate optimal solutions for infinite horizon optimal control problems. So we can actually use this for solving problems which are otherwise very often computationally intractable, at least in an approximate way. Here are two recent surveys I have co-authored or authored, which have just appeared a couple of weeks ago. These both, one is a chapter in the Handbook of Numerical Analysis, which focuses on the Turnpike property more and gives actually more than I told you here, gives you additional discrete time and continuous time results. And this is a paper which focuses more on dissipativity, but of course, due to the close relation, Turnpike property is also very prominently featured in this survey article. Yeah, with that, I'm finished. I thank you very much for your attention. And if there are any questions, I'm very happy to take them now.
Yeah, thanks for the talk. I think I take over. So do we have any questions? You can just speak up if you want to. There is a question. It will be typed, so somebody doesn't seem to have a microphone or something. As you take n big, the epsilon ball around the equilibrium gets small. Is there a known bound on apps based on n? I guess this is probably on the last result that you presented, because
there is a known bound.
question.
Actually, this is the whole derivation of this epsilon is constructive, but of course it depends on many other quantities which may be difficult to determine precisely. So I think the most important thing is that under certain under certain bounds, which are quite easy to check, we know that this goes down exponentially fast in n. So it's like a constant times e to the minus another constant times n, capital N. And this is very important because this really tells you that it goes down very, very quickly. And this is also what we see in our examples, in the simple ones, but also in more complicated ones, that usually for many problems, you do not need to choose n very large to get a reasonably good performance. There are some problems where this is not the case. And this is then when we typically try to look at problems, at optimal control problems with terminal conditions, then terminal conditions become important. So if this epsilon 1 shrinks too slow, then you get into trouble. Then you get trajectories that go into some completely different way. And this needs to be avoided then.
Yeah, I mean, I have a couple of questions. Maybe I ask one, and if there are other questions, then I take them after that. So how, because I mean, there's always a gap between theory and practice, especially in control, I guess. So how relevant is this in practice? I mean, can you really check that the system has the Turnpike property? Because I mean, yeah, you would like to. The person says thank you, and so you yeah, because I mean, let's say somebody comes with an industry problem. How likely is it that you can verify this thing has the Turnpike property?
Yeah, of course, rigorously quite difficult. So let me tell you two problems where we have worked on. So one is actually one where I just started working on. This is a quite simple problem. It comes from biology. It comes from modeling of some genetic translation process. And it's a very simple class. It's a whole class of models, and this is the very simplest instance. And actually, what one can prove using completely other techniques than I presented now is that if you only look at periodic solutions, then actually the only good solution is an equilibrium, which is a particular periodic solution. And also that all other solutions converge to this equilibrium. So we have a kind of Turnpike property for that. And I thought, well, yeah, then we should probably try. Then we know that the storage function exists, so this Lyapunov-like function. And then it should, since the problem is really not difficult, it just has a couple of terms, at most quadratic, it should be possible to write that down. Well, I spent 2 or 3 hours on that, and I wasn't immediately successful. And I mean, of course, maybe this is because I didn't try the right approach, but this already shows that like finding Lyapunov functions, finding the storage function can be difficult. And then this means that we also have to work on, yeah, that we have to kind of work around this, find some other solutions. So we really had an industrial project also. This was on gas power plants, on optimal startup of gas power plants. And these were models actually with hybrid components, so discrete, continuous, with integer variables in their dimension beyond 50 space dimensions, and no way to check any of this rigorously. But what you can always do is you can simply solve the optimal control problem numerically and see whether the Turnpike property holds, right? Because this is very easily seen. If all the solutions come together and move together to a certain point, then you are quite sure that the Turnpike property holds. And of course, this doesn't prove anything, but it gives you quite some confidence that model predictive control should work well. And actually it worked very, very nicely in that example. So in practice, you need to do things numerically. There are also numerical approaches to compute storage functions. There are also numerical approaches that compute them on the fly while MPC is running. All this is there. In this plain theoretical form, it's probably hard to apply to real complicated examples, but you can get guidelines from there, you can get intuition from there, what can we expect under certain circumstances, and I think this is the value for real practical examples in this context.
Yeah, so your preferred method would be to really have a storage function. And
that would be ideal. In this example, we would particularly find a storage function for the whole class of systems. And I wanted to start with the simplest one and in the hope that there is an idea how to generalize these for the larger class. But so far, not successful. Let's see, but I will keep on trying.
Yeah. Okay. Do we have more questions? So if yes, then please unmute yourselves and just talk. If there are no questions, well, then I ask my second question, because, I mean, what you are basically saying is you have an initial phase where you go to the equilibrium, provided you have the Turnpike property. You want to go to the equilibrium, then you want to stay there, and then you want to go away. Isn't that basically almost like a soft bang type thing? Isn't that very related, and would that give some opportunity to do something theoretically?
I wouldn't agree to that, because usually the control, which this is maybe something I should change in this talk. I didn't show you the controls. The controls, they do not go bang bang. They go down in the first example, and also in the second, they go down smoothly to an equilibrium value. And in the first example, they stay at 0. In the second example, the controls then also have the same shape. And this is a continuous development. It's not bang bang.
Okay.
But there are actually there is a variant of the Turnpike property called exact Turnpike, and this is when the solution is not only near to the equilibrium but actually reaches it in finite time, stays exactly, and then leaves it again. And I would agree, this is quite close to bang bang. This is also usually related to L1 functionals, so L1 costs, which enforce this behavior, and they also enforce that only the extremal values of the control are optimal, right? So at least there is a tendency for that. And in that sense, yes, there is this relation, but for the setting that I had, it's not classical bang bang. It's somehow phenomenologically similar, but it's not classical bang bang.
Yeah. Okay. And then I have a quite theoretical question. The behavior that you mentioned, which at first sight is very strange, that somehow you would think that the errors increase as time increases. You had this in the sensitivity example.
Yes.
And basically there's also something coming back from the end that is increasing, and it's somehow counteracting. So you basically you have exponential expansion in one variable forward and in one variable backward, and exponential expansion of the errors. This reminds me a lot of hyperbolic shadowing.
Yeah.
Is it that?
Yes.
Is it related?
I'm not. Oh, I looked into shadowing many years ago. I do not recall the technical details, but it's very, very similar to a hyperbolic situation, because essentially what you have, if you say you have a one-dimensional example, so you have a one-dimensional state which you plot on the vertical axis and a one-dimensional co-state which you plot on the horizontal axis. And then how would the Turnpike trajectory look like? It would look like a trajectory which moves to a hyperbolic equilibrium, which sits where the axis goes, stays there for a long time, and then moves away again. And you can easily see that if you perturb a little bit, then this, while staying close to the equilibrium, somehow the perturbation tends to be forgotten, and then it moves on and you don't see that anymore, right?
Yeah.
And this is precisely what happens. And if you ever heard Emmanuel Trelard talk about turnpikes, he would always show this, or he would often show this picture, because this is his way of explaining what happens. So yes, I think there is a relation to that.
Yeah. So that's where I thought maybe it's even the same thing.
Maybe it's the same thing, but the thing is that here we always have this particularity that we need to determine the optimal control before we can talk about what's really happening, right? So it's not an autonomous problem, but it's a problem where we have an additional degree of freedom which first needs to be determined. This is what makes it difficult.
Yeah, what I would think is, I mean, if you look at the flow that's induced by the optimal controls, and then basically you consider a perturbation in the control, a perturbation in the dynamical system.
Mhm.
You're basically saying you're making a mistake, or you're making, yeah, that's basically what I mean. And then it may be actually the exact same thing, but I'm not sure. I haven't seen the structure of the, yeah. So that's why I think maybe it is actually the exactly same concept as hyperbolic. Hua, do you want to ask that yourself? Or
Yeah.
is there, yeah, okay.
Yeah, it's a very naive question. I'm not working in optimal control, but I think it's quite an extension of the neighboring extremos in optimal control, right? Where there's a perturbation in the starting point of the initial state.
So we do not exploit these neighboring extremos explicitly, but I think it's connected. I mean, what we did in the sensitivity are linear problems, and then of course this is all. It simplifies, of course, but yes, it's. I think it's very related. Yeah, I could not tell you the technical details now, but I think there is a connection.
Yeah, but if I mean, then I have a question, because when I apply, because neighboring extreme, I have a explicit formulation when, I mean, not very explicit, but when your initial point perturb a little bit, then you have a formula to recalculate the control. But then if I apply some numerical methods like discretization method, then actually the computation is different, and maybe the formula different. So I'm not sure that for your methods, for your then apply something like discrete, like numerical methods, whether the results still remain or.
So we actually we did a lot of numerical simulations for this PDE setting, where of course we need then to employ first space and then time discretization. And we checked the sensitivity in space and time. And actually what we also did is we also considered then the numerical error as this epsilon, right? So we interpreted the numerical error as the perturbation. And numerically, we could confirm everything we can prove. So it works very nicely also numerically. And what is particularly nice is that if we want to do MPC, we only need the first piece of the optimal trajectory. And so what this means is, if we treat the numerical discretization error as the perturbation, this means that at the end of the time horizon, we can use a large, we can actually allow for large errors. And this is something that we could really confirm numerically, that if we use a grid, which is fine in the beginning and then gets coarser and coarser, produces a very, very good closed loop solution, which is could be better than where we use a fine but not extremely fine grid, which is uniform on the whole time horizon. We have a whole paper on that, which just appeared in the Science Journal of Scientific Computing, where we checked this. And I think there's no problem here by going to numerics, because the fact that everything is robust also explains why it's robust under perturbations that come from numerical discretizations.
Okay, yeah, thank you. Thank you for your answers.
Yeah. What is a neighboring extremal?
It's just a, well, I think it's a theory based, just like sensitivity analysis that Lars explained, but then there's only about to compute a new solution if the initial it changed it, yeah, so that we don't need to recompute the whole control. So
I think you can speak like a Taylor expansion of the optimal control and the optimal trajectory. Right? As a topic analysis, if you perturb your initial condition a little bit, how does the optimal control and the optimal trajectory change? And you can write this as a series expansion then.
Yeah, exactly. This assume that, well, the change, the new solution doesn't still close to the previous solution linearly, like use just the first linear Taylor expansion. And then they calculate that matrix, and then you recalculate the control. Yeah, okay. That's what I said anyway.
Yeah, thanks. Okay, do we have more questions? If not, then thank you very much, Lars, for coming.
You're welcome.
Yeah, nice talk. Many nice pictures that really help understanding. And yeah, it's a bit strange. I always feel very strange to close these sessions. Goodbye to everybody.
Bye.
It's really strange because yeah, because I mean usually there's some you go to lunch or something, whatever, and these sessions they end with end of the electricity, something like that.
Okay, wieso kriege ich, hier hat sich irgendwas geändert. Ich kriege jetzt gerade die Freigabe gar nicht. Ne? Ah,
Wie, hast du keine Erlaubnis?
Ja, ich habe den Knopf gesucht. Okay, mach's gut.
Okay, ja,
Kann ich
du auch,
jetzt
ne?
zusammen was essen gehen, aber das geht nun leider nicht. Ne?
Das geht nicht. Okay, ja, dann ja, mach's gut. Schönen Tag noch, ne?
Gleichfalls. Ciao.
Bis dann.